Okay, so we left off last class. My PowerPoint is really being happy right now. Talking about ions and electron configurations. And we talked specifically about how electron configurations of covalent molecules, those atoms involved in the bond, try to acquire a noble gas electron configuration in their valence shell by sharing the electrons. Whereas when you have ions, ions tend to either fill their valence shell by taking electrons away, making an anion, or vacating those valence electrons, just getting rid of them so that they go down to the core, which also has a noble gas electron configuration. So when we look at some ions, we'll talk about some ions and what the idea of ions being isoelectronic, which just means that they have the same electron configuration. And we'll look at some isoelectronic ions in just a minute. But one thing to keep in mind as we go through some of the next pages worth of calculations, examples, etc., we're really going to focus primarily still, remember, on the main group, right? So group 13 through 18, right? And then groups 1 and 2. So those are the ones we're primarily focused on here. You can talk more about transition metals in the Chem 102 class. But what you'll notice here in this particular image, and these are measured in picometers, and there aren't any numbers here. We've got some numbers, or there aren't any numbers in this periodic table. You can see numbers for the ionic radii over here in the table at the bottom right. What you'll notice is the green atoms represented here, right? Those green atoms are the actual atom, it's the neutral atom. If they are red next to it, right? So this is that green. If we just look at beryllium, the green is the atom. The red, right, is the ion, or blue. Okay, that's going to be your ion. Okay, when I say red or blue, well, red is representing cations, and blue is representing anions. Okay, and so if you compare the size of the green atom to a cation, so if you look at beryllium, beryllium has a cation that's going to be smaller than the beryllium atom. Boron has a cation that's smaller than the beryllium atom, right? Carbon has a cation smaller than the beryllium atom. You'll notice all of the cations are smaller than their parent ion, okay? But all of the anions, if you notice and look at nitrogen, right? Nitrogen, right, is much larger. Its ion is much larger. So the anion is larger than its parent ion. And so we're going to utilize some isoelectronic ions in order to talk about sort of why this happens. Right? Why is it that an ion, if it's an anion, will be bigger than its parent atom, whereas a cation will be smaller than the atom? And so we're going to do that with a few different atoms and ions. Okay, so the ones we're going to look at, we're going to start out with nitrogen, oxygen. One second. Okay. So nitrogen, oxygen, fluorine, sodium. Oh, sorry, excuse me. We'll do neon as, although it doesn't make an ion, we'll want that there as a comparison. Sodium. And do we want to do? Yeah, we'll do magnesium also. We don't need to, I think that's sufficient for us, but we'll throw it in there for good measure. We don't really, I'm not going to do aluminum though. So what I want us to do here is first off, think about the atom. So the atom, when we think about the atom, so if I think about nitrogen, okay, so with nitrogen, right, that's going to have a total of, if we look at the number of protons, I'm actually going to move my in down a little bit. Number of protons and the number of electrons in just the atom, and we're going to compare that to the ion. Okay, so the ion will do the number of protons and the number of electrons as well. Okay, and so you can kind of look at it as, here's our atoms over here, those are atoms. Over here, we're going to have ions, okay? So starting with nitrogen, well, nitrogen has a total of 7 protons, and it's a neutral atom, right? We're talking about an atom, so it's neutral, so it'll also have 7 electrons. But the nitrogen ion is in 3-, so it'll have a total of still 7 protons. That's why it's nitrogen, right? The number of protons determines the element. But if it's an anion, it's going to gain the number of electrons associated with that negative charge, right? So this will gain 3 electrons and have a total of 10, okay? And so the other thing we can do for our ion is we can sort of look at the electron configuration, okay, of that ion, okay? And if we think about nitrogen, we've got 10 electrons, so it's going to be 1s2, 2s2, 2p6, okay? Or helium, 2s2, 2p6, if we want to do the abbreviated electron configuration, okay? If we look at oxygen, oxygen has 8 protons and 8 electrons. Oxygen's ionic charge is going to be 2-, and so it'll have 8 protons still, but it'll also have 10 electrons. So you'll notice, right, 10 electrons in both of these when they become an ion. So it's going to have an electron configuration that's also helium, 2s2, 2p6, right? Those are the same, right? So those are isoelectronic, right? Those ions are isoelectronic. So nitrogen and oxygen are isoelectronic ions. If we look at fluorine, fluorine has 9 protons, 9 electrons, but fluorine as an ion is going to be F-. It's going to grab onto 1 electron, so it'll still have 9 protons, and it'll have 10 electrons, just like oxygen, O2-, and nitrogen's in 3- ions. So it will also have an electron configuration that's the same as helium, 2s2, 2p6. And then we come to neon. Well, neon has 10 protons and 10 electrons. It doesn't really have it does not have an ion that we associate with it. Yeah, you can cause neon to be ionized in a laboratory under harsh conditions, but we're really rarely ever going to see that. And so what we can do with that is say, okay, well, the electron configuration of neon, just a neutral neon atom in this case, is helium, 2s2, 2p6. So all 3 of those ions above are also isoelectronic with the neon noble gas atom. If we go to the next row, we have sodium, and sodium will have 11 protons and 11 electrons, but a sodium ion we know is sodium plus, and so it'll have 11 electrons, but then it gives up it has 11 protons, but it gives up an electron, so it only has 10 electrons, which means that, well, if we considered the sodium atom to have an electron configuration, right, of, in this case, it's neon with 3s1, well, then the sodium ion will just be neon. Hey, turns out It's isoelectronic with neon. Okay. And magnesium would have, as an atom, 12 protons and 12 electrons, meaning it would be neon 3s2. But magnesium has a +2 charge, so it'll still have 12 protons, but it'll also have 10 electrons. And so it has an electron configuration of neon. And you'll hopefully notice when I write down the electron configuration of the cations, I'm happy writing down an abbreviated electron configuration because I've removed, if you will, change my color here, right? So I've removed those valence electrons, right, from both of those cations. And so we can say, oh yeah, well, its electron configuration is the same as neon. But when it comes to neon itself, we have to write its abbreviated electron configuration properly, which has a core of helium and then the 2s and 2p valence electrons. And so although they're written differently, they are isoelectronic with each other, okay? And so these all have one thing very significant in common, right? The same electron configuration because they have the same number of electrons, okay? Now, when it comes to size, okay, so the size is a key thing that we can compare here. If we look at the number of, so we'll go back up to nitrogen, look at the number of protons to the number of electrons in the nitrogen atom. When we compare that to the number of protons and the number of electrons in the nitrogen ion, right, there are way more electrons in the nitrogen ion. So one way that you can start to think about each of those electrons in a given atom, the electrons feel, if you will, right? They don't really feel, they're not living beings, but they feel the pull of a certain number of protons. Right? Because there's a certain number of protons in the nucleus. So if we were looking at in versus right in 3-, and you can compare these by just saying the number of electrons divided by the number of protons is a good way to compare this. For the nitrogen atom, you would have 7/7 equals 1, okay? For in 3-, you would have 10/7, right? And so that's going to be a value that's much greater than 1, right? And so with that in mind, well, that means those electrons aren't being held in as tightly, they're spreading out more, and so the size of a nitrogen 3- will be larger, right, than the size of the nitrogen atom. Okay, so, and that's kind of a key there, right? That's just comparing the size of a nitrogen atom to the nitrogen ion. And in that case, you can do the same thing for something like sodium, right? Sodium versus sodium plus, right? With sodium, you'd have 10/10, right, equal to 1. With the sodium ion, you would have, 11/11. What am I doing? There we go. 11/11. With a sodium ion, you would have 10/11, which is less than 1, and so that sodium ion would be smaller. Okay. Now, the other thing I can think about here is you can think about this from a standpoint of, well, if I compare two different ions, which ion will be bigger, which ion will be smaller? And so if I wanted to compare, say, the fluoride ion versus the magnesium ion, okay? For the fluoride ion, I would look at the number of electrons would be 10 divided by the number of protons, which would be 9. So that value right there is greater than 1. Whereas with magnesium, the number of electrons in the magnesium ion is 10, but it would have 12 protons. And so that value is going to be less than 1. And so the fluoride would be the larger ion, and the magnesium would be the smaller ion. So you can sort of qualitatively compare their sizes fairly easily just by looking at the number of protons and the number of electrons. And the whole reason is, if you look at, and again, I'm going to go back to the nitrogen ion and the nitrogen atom. If you look at in the nitrogen atom, each electron feels the pull of about 1 proton. Whereas in the nitrogen ion, each of those electrons feels the pull of less than 1 proton, because there are 10 electrons and only 7 protons, right? And so that's going to mean those electrons aren't held in quite so strongly. And so it's going to give you a bigger radius as compared to the neutral atom. Okay? And so you've got some idea of why we have sizes of ions that are larger or smaller than the parent atoms themselves, right? Anions are going to tend to be larger. Cations are going to tend to be smaller than their parent atoms. So the other thing we're going to look at is the energy effects in an ionic compound. And we needed to know the size of those ions, because when it comes to the energy effects in an ionic compound, we can talk about this lattice energy, okay? So if we think about just some 2 neutral atoms, for, in this case, sodium chloride, and those 2 neutral atoms going and making a sodium chloride ionic substance, okay? There are a couple things at play here. If you look at sort of the energy difference between the two, right? The sodium chloride ionic compound is much lower in energy, right? It's more stable, it's lower in energy than having sodium and chlorine atoms themselves. But to get from a sodium atom and a chlorine atom to sodium chloride as a compound, you've got a couple things you need to do. The first thing is you go up in energy when you cause those atoms to be ions. So you can think about this from the standpoint of the ionization energy of sodium, right? It gets ionized by losing an electron. But also, if you look at chlorine, right, chlorine gains an electron, so there's the electron affinity. These are the things we talked about back in Chem, or in chapter 7. And if you look at the electron affinity and the ionization energy of those two things, it turns out it's a little bit less stable to have 2 separated ions. Now, notice that the state of these ions, they're both in the gas state, right? They're both in the gas phase here, right? We're just saying, hey, these 2 separate atoms become separate ions in the gas phase. They're separate from each other. But the thing that happens after that, and this is the really big stabilization, is those ions, are a cation and an anion. When those cation and anions come together, right, they really want to stabilize. They form the solid. And so they come together and they stabilize. And that is what we call our lattice energy, or the energy that it takes, in this case, the energy that's given off when these 2 ions come together and form the solid, okay? And the energy that's associated with that attraction can be calculated using this equation over at the right, okay? Where you have the energy of attraction is equal to a constant, 231 attojoules per picometer, times Q1, Q2 over D, where Q1, okay, Q1 will be the charge of the sodium, right, which is, of course, +1. Q2 is the charge of the chloride, which, of course, is -1. And then D is the distance between the nuclei, right, or the bond length, if you want to look at it that way. And what we get for that D, okay, the D there is going to equal the radius of sodium ion plus the radius of chloride, okay? And so we're going to take this stuff and we're going to actually plug it in as we calculate that lattice energy. So we've got our equation here. Okay. We've got our, so we can say the energy, right, this lattice energy is equal to 231, so attojoules times picometers. So an attojoule, right, that A is 10, so times 10 to the minus 18. So this is 231 times 10 to the minus 18 joules times Q1 plus 1, Q2 minus 1, divided by D. Now, what's that D? So D, what we can do is we can go find our ions in this table. So sodium, 102, chloride is 181. Make sure we check our table. Our table is measuring these in picometers, so that's good. Because that's nice here, we can just plug that value into there, right? A picometer. Okay, so the P says times 10 to the minus 12. And so the distance there is going to be 102 picometers from the sodium ion plus 181 picometers from the chloride ion. Okay. And so that's going to give us a value of 283 picometers. And so we can now plug that in. So we say our energy will equal 231 attojoules times picometers times plus 1 times minus 1, right, for the charges of sodium and chloride respectively, times, or divided by 283 picometers. And our picometers here will cancel out. We'll be left with a value of negative 0.816 attojoules for the energy, this lattice energy of these ions. Okay, and so here that's basically, if we go back up to this question or this page up here, you can see that's the value that we had in this step 3, right? It's the energy of attraction of those ions to each other. Yes, Maya?
Is it 283 times 10 to the negative 18 as well, and they just cancel out? I'm just like sure.
No, the attojoules doesn't cancel out. That's just, so this would, you could also say that's equal to negative 0.186 times 10 to the minus 18 joules, or is equal to negative, what did I do? Apparently I'm dyslexic, which you probably already know because you've been in the class. So, or you could say it's negative 8.16 times 10 to the minus 19 joules. So those are all equivalent values to each other. Right? Just atto is one of the prefixes I didn't make you guys memorize. All right. And so that's sort of how you would calculate these. Now, there are other ways of representing the size of the ions, and that's what I have in the next slide. It's just the same idea that we had above in the periodic table above. In this case, what we have here is the gray is for the atom, and the pink is for a cation, and the blue for an anion. Okay, and you'll notice sort of this comparison is kind of nice and easy to see, right? All of the anions, right, oxygen compared to, so the oxygen anion versus the oxygen atom, right? Oxygen anion is bigger. If we look at, say, the potassium ion compared to the potassium atom, the potassium ion is smaller. And so all of these units here for the bond length there, those are actually measured in what are called angstroms. Okay, and so this is the this unit here is called the angstrom. Okay, and an angstrom is just one. So 1 angstrom is equal to 1 times 10 to the minus 10 meters. So it's 1/10 of a nanometer. And the reason that this unit exists is actually because of the size of atoms. And so in this particular table, you'll often see angstrom as a unit for the length of, or the radius of an atom, or the bond length of something, because that's the scale that bonds tend to, and atoms tend to be, and bonds tend to be, okay? And so with that in mind, we're actually gonna end here, and tomorrow we'll pick up with ionic and covalent bonds, or rather, the ionic character of covalent bonds, and we'll see how ions and covalent bonds are really related to each other. We're going to find that's through the electronegativity difference. And so that's what we'll cover for our lecture material today.